match. So I'm going to go ahead and pause my tape and fill these in, and then I want you to do the same. So hold on. Okay, what I did so far is filled in the right-hand column. Now, I'm going to put each of these in my calculator and see which ones they match with. So if I put log of 4, now just a reminder, when I put that in, I want to close the parentheses behind the 4 so I can put the log of 2 next. And that will tell the calculator to be very careful. Now, the thing I want you to think about, what do you think this is going to be? Now, some might guess it's going to be log 6. Let's find out what it is. I get 0.903. 0.903 is actually the log of 8. Now, if I put in log 4 plus log 5, I end up getting 1.301, which is log 20. It looks like instead of adding those arguments, when they combine into one logarithm, we multiply the arguments. So what do you think would happen if we're subtracting logarithms and we combine them into one? You're absolutely right. We're going to end up dividing. This would be the log of 3. 2 log of 3. It ends up being the same as log 9. 3 log 2 ends up being the same as log of 8. And let's think of why this is true. 3 log 2, that really means log of 2 plus log of 2 plus log of 2. And if we're adding the logarithms, we combine them by multiplying. So that's 2 times 2 times 2, which is really 2 to the third. So there's these little properties, these little rules that help us simplify or expand logarithms. So we want to go through these and practice this because this is really important skills. If I add 2 logarithms, I can condense them into one logarithm by taking those 2 arguments and multiplying them together. If I have 2 logarithms that are being subtracted with the same base, I can combine them into one by dividing their arguments. Now we notice on this one, when there's numbers out front, that doesn't mean I had it written that many times, so when you got it together, it was like having that argument to the power of C. And if we look at one of these, we can really show the rules. Let's let that first logarithm equal m and the second logarithm equal n. We can always rewrite a logarithm as an exponential. Here's the base to that exponent, gives me that answer. That base to that exponent gives me that answer. So we're good so far. Now, let's look at that right side. Log of b of a times c. Well, this is going in for a, and this goes in for c. Is everybody with me so far? Now, the bases match and you're multiplying 2 exponents. You add your exponents. That's m plus n. Well, look, we learned that rule about these bases match. You just get that exponent back. So you end up just getting back m plus n. This is an algebraic proof to prove that first property. But we saw that it was true using our calculators. Now, one of the reasons we used this a long time ago is we didn't have calculators that gave us logarithms. So we had to use basic logarithms that we already knew and find ways to combine them to get our answer. So like we would know maybe what 3 was and maybe what 6 was, a log of 6. But we wouldn't know 18 because they wouldn't give us that in the table because you can actually figure that out using stuff you already have. I know that 18 can be made up of 3 times 6. Now if we look back at our rule, that kind of reminds me of that first rule on multiplication. They're combined together with multiplication. So we can uncombine them, or expand it, to be log base 4 of 3 plus log base 4 of 6. Well, I happen to know what log base 4 of 3 is. It's 0.792. Log base 4 of 6 is 1.292. And then I can just add those two together. That's 0.792 plus 1.292. And we get 2.084. Let's look at the next one. How could we combine somehow 3 and 6 to get 0.5? Well, 0.5 is 1/2. That's really like having 3 divided by 6. Look at the rule. Single logarithm with division can be rewritten as 2 logarithms with subtraction. So that would be 0.792 minus 1.292, which ends up giving me a negative 0.5. All right, let's see if we can figure out 81. 81, 3 times 27. Hey, isn't that 3 to the 4th power? It is. 81 is really 3 to the 4th power. Now, if we look at this neat little rule, it said that we could rewrite that as the 4 out in front. Now, we know what the log base 4 of 3 is, 0.792. So all we have to do is multiply 0.792 times 4, and we're done. All right. Now, to solve problems using logarithms, there are times where we need to condense things into one by using those 3 properties. And sometimes we want to expand them, so like we did up here, into several different logarithms in a row. This is an expanded expression. We want to condense it into one logarithm. They all have the same base. So let's go through our order of operations. Parentheses, only parentheses are around the arguments, that's okay. Next one is exponents. This 2 can go up here and become the exponent. So end up with log of 6 plus log of 2 squared, which is 4, minus log of 3. Now, addition combines into multiplication, so this would be 6 times 4, and then that turns into division. 6 times 4 is 24, divided by 3, I end up with just the log of 8. Let's see it on the next one. Exponents first. Numbers in front become the exponent of that argument. These two are going to get multiplied, right? Log base 4 of 20 times, that's going to end up giving me an x to the 4. Now I'm subtracting log base 4y, so when it condenses, that will be division. Exponents go up. Maybe I'll take I got a little bit more space here. We'll do this one step by step. This is log base 2 of 20 plus log base 2 of x squared minus log base 2 of 3 minus log base 2 of y cubed. These are being multiplied. So in our new logarithm, they will be multiplied together. Now I divide by each thing I'm going to subtract. So I'm going to divide that by 3 and by y cubed. So anything being subtracted will end up in the denominator. Anything being added will be in the numerator. Now how can we do this backwards? What if we have one logarithm and we want to write it as a series of other ones? We want to undo each of those operations. Now, we did exponents first, then multiplication and division, which turned into addition and subtraction. So we want to do the opposite here. These are being multiplied, so to undo it, we will add them. We also want to undo any exponents in here. Exponents end up going out front. So that's going to be log of 3 plus 4 log of x. Now these are in the numerator. They're the ones being multiplied, so those would get added. We can actually do this all in one step, couldn't we? And I'm going to start writing my logs in cursive to save time here. That's log of 2 plus log of x. Now since this is being divided, we're going to subtract by log of y squared. But wait a second. I could save myself a step, and instead of writing squared right there, why don't I just put the 2 in the front? See what we have here. Log base 7 of 7 plus log base 7 of the square root of x. I'm writing it like that 7 times. Both of these are being divided, so both will be subtracted. Log base 7 of y squared, I can go ahead and put that one there, minus log base 7 of z. Now I want you to be very careful here. Anytime you actually know something, you want to go ahead and simplify it as much as possible. Do we know the exponent that 7 would have to go to get 7 back? I hope you do. That's just 1. Now what is the exponent that gives me the square root? That exponent is 1/2, so it goes in the front. And now we have something that is as simplified as possible. Now, there also were a couple of problems on the pair work that I want to go ahead and talk about here so that when you see them again, you would know how to do them. Let's say I have log 1/8 of 9 times log base 9 of 2. Now we're multiplying these. We do not have any properties that say anything about taking 2 logs and multiplying them together. So the hint is, let's change the base on the second one. I'm going to leave the first one just like it is. What I want to do is use the change of base formula to change the base of the second one to be the same base as the first factor, the first logarithm, so that it has these bases. Now remember, the change of base formula says log my new base of the original argument divided by log with the new base of my old base. Your old base goes in the denominator. Now, since I'm nice, these usually work out pretty nice where these end up dividing out. So now I'm just left with log base 1/8 of 2. Now a lot of times we really want to make sure that if we can figure this out, we want to. So this question, this is really asking us, remember if I put something there, that's like saying 1/8 to what power gives me 2? Well, I know 1/8 to the 1/3 power would give me 1/2. That means the cube root. But I don't want 1/2, I want just 2. So that exponent had better be negative. So my whole problem ends up just giving me negative 1/3.